Okay. It's Wednesday, and the name of the day is equilibrium. Equilibrium means something very specific in the context of forces. When we talk about equilibrium, it doesn't matter what kind, we mean that F net, that is when I add up all the vector forces, I get zero. Zero means zero acceleration. So all the forces, if there are any, come together to balance. This does not mean there are no forces, it just means that they balance. And again, don't forget, they're vectors, so they act like vectors. In this chapter, pay close attention to the two kinds of equilibria, static and dynamic. Make sure you understand the distinction between them. We're not going to worry about rotations yet, so if you're thinking about that, about objects tumbling, don't. We'll get there, but just not right now. One of the things you're going to have to be conversant in is how I take this equilibrium condition, and if I specify a coordinate system, let's say the typical one, x and y, Newton's second law is really two equations. Well, it's three in three dimensions, but we usually restrict ourselves to two. Really what this says is that I have a separate condition that the sum of the forces in the x direction is zero. That is, the components of all the forces in the x direction cancel. And F net in the y direction is zero. Okay? So when I do this, any components that point, let's say the x components, every component that points to the right is positive. The components that point to the left are negative. You're going to become really good at this, but make sure that you practice hard. You're also going to be really good at identifying normal forces, okay, contact forces. Now, normal in the sense means perpendicular to the surface. Okay, so don't forget that. Also, don't forget that weight is a force. Okay, mass is not. So if your mass is 75 kilograms, that mass is the same everywhere, but you weigh different things on different, say, planets. Okay? You would weigh more on Earth and about, you'd only weigh about a sixth of what you weigh on Earth on the moon. Okay? So let's be precise about what we mean by weight. In this chapter, we finally figure out where our acceleration due to gravity comes from. Okay? So make sure that you sort of identify that derivation. It's quite easy, it's quite simple. But our kinematics, projectile motion, it all comes from using Newton's second law with the appropriate free body diagram and finding out that the acceleration is negative g, particularly if these are coordinate systems. The examples are pretty good. Okay, pay very close attention to how the coordinate system translates into sort of your quantitative analysis. There's one example here that I really do like. So in the slides, you'll see that there's this nice example of thinking about how we hang a traffic light in a goofy fashion. Okay, so in this slide we have a picture, the physical picture, and a strategies outlined. Right, that we're going to establish a coordinate system. I'll show you on the next slide. We're going to then break our forces down. We're going to use Newton's second law, that is, apply the appropriate equations, and solve for any unknowns, that is, do the algebra. Okay. Now, the important thing to note here is that in equilibrium, this is a static equilibrium case, the acceleration is zero, so all the forces add up in the two components. Now, when we look at the analysis, it's interesting here because we're actually thinking about these aren't free body diagrams, but they're showing you two different objects, and I use objects in quotations. The first one, well, that's just the light. Okay? So if you look at the two forces acting on this object, you have the tension acting upward, pulling up, and gravity pulling downward. So in our coordinate system, the tension acts in the positive y direction, and gravity acts in the negative y direction. But we've also done, in this case, a free body diagram on the point connecting the three ropes. So we can do that. The mass is zero. That doesn't mean, that doesn't really matter because the acceleration is zero as well. But we use that as our object, the point where the three ropes meet. Okay? So there's some angles indicated here. Make sure that you can do that geometry there to convert the angles from the previous slide to the angles in this one. But essentially what we're going to do after we draw this picture of the three ropes on a knot, we're going to use Newton's second law in both the x and y directions. So play around a little bit, have some fun, take your time, and make sure that you come with any questions.